Okay, so this is Stats XL13. The website is it's myuclaextension.edu, and that's the Canvas website. And when you log in, it should look something like this, and you should be able to access the XL13 on Canvas. Okay, and under modules you'll find all of our stuff. Oh, I should remove these ones. These are videos from last quarter. And you'll also see the syllabus, and so I'll just kind of briefly run through it. My email address is this. You can send me emails. I teach 4 statistics classes, so in your email make sure you write XL13, so I know that you're talking about this class. Just because if you say I'm in your statistics class, that doesn't help me out. I mean, I'm sure you guys are taking only one stats class, but me teaching 4 of them, I won't know. I still won't know which class you're talking about. So make sure you write XL13 somewhere in there. If you have any administrative issues, the person you need to contact is Sue Kwan, and her contact information is here. So you know, I don't take attendance or anything like that, but if you're going to be absent on the day of a quiz or something and you need to request a makeup, or if you get sick or anything like that, send Sue an email, let her know your situation, and she will be the one to either approve or deny your request for a makeup or something like that. Okay, so she'll handle all of the administrative stuff. If any of you have a learning disability or anything like that, you need special accommodations, you can ask Sue, but there's actually a department at UCLA Extension that handles that, and the lady you'll talk to there is Pam. But you can ask Sue for her contact information. Well, here's just a big list of topics. The textbook that we will use is this one. The 4th edition is green. That one's also good. In terms of material, I'm not sure what changed between the 4th and 5th edition, to be honest. I think they just renumbered the problems and maybe moved things about. But you know, I was flipping through, at least in the pages and the content, and I'm not 100% sure what changed. So you know, you might be able to save a few bucks getting the 4th edition. There is a optional book that I don't really reference, but I do recommend it if, especially if you're pursuing something in like the health sciences or something like that, and that's this book called "What is a P-Value Anyway?" It's published by a textbook company, so you know they charge this ridiculous price, and it's just kind of like this thin little paperback thing that should probably only cost $6. So you know, maybe you can get it used, but yeah, it's just anyway. That's how Pearson makes their money, by renumbering textbook problems and releasing a new edition. So anyway, that's what we have going on. You'll need a computer. I'm assuming you guys have access to a computer and you can install some software on it. Where there's going to be a few labs where we use this software called R. It's a computer statistics software. It's free, and it will run on Windows, Mac, Linux. The only thing it won't run on is like a Chromebook. If you have a Chromebook, then you'll need access to something that you can install things on. Okay, we'll have a midterm and a final and some quizzes and homework and lab assignments here. Okay. Are there any questions so far? Okay, and so actually, the homework, it says homework and lab assignments 15%. I have homework listed, and homework will count for 5% of your grade, but I'm not going to actually collect homework, okay? So I assign it for you guys to do and learn from, but I'm not actually going to collect it, and at the end of the quarter, I'm going to just give everybody their full 5% for the homework. So the only thing you'll turn in will be the lab assignments, and that will count for 10%. So I mean, I guess you could get away with not doing the homework, and I won't know any difference, but it will show when you take the quizzes and exams. So definitely do the homework there. Okay. A lot of the so these homework problems I've done, and for a lot of them, maybe not all of them, I've either posted solutions as text, or I've made little videos of myself working through the answers. So they're there to kind of make so you know if you're doing the problems correctly or not. Okay. I'm recording this screen, and barring any technical glitches, I'll post it up onto YouTube and add a link to the site. So actually, these links are outdated, so I'll have to I'll get rid of these ones and put them up. Okay. Questions? Are we all good? Yes. No, the numbers are different. So for most of them, I've said here are the exercises for the 4th edition, and here are the exercises for the 5th edition. Like they might have added or taken away a few of the problems, so maybe it's not like 100% correspondence between problems, but I'd say 99% it's fine. Okay. Okay, well, with that, we'll get started then. Okay. So I'll usually leave this front row of lights off. So if you're sitting in the front and you need more light, you can always move back a row. And those of you, I mean, if you guys can see fine in the back, then you're fine. I'm not going to force you to sit closer, but I think. It's easier to stay engaged when you're a little bit closer. Okay, so we'll get started. So this is statistics. Okay, and this is so intro stats. This is my favorite class to teach. It was my favorite class to take as an undergraduate student. It literally changed my life. I was an engineering major. I finished my degree in engineering for undergrad, and then, but after working for a few years, I decided to come back to graduate school, and I decided to study statistics because I enjoyed my statistics class in undergrad very much, and I ended up taking more statistics classes in undergrad, and because I loved it so much, and here I am. Now I'm teaching statistics. This is my dream job of teaching statistics at UCLA. So I teach full time on main campus, and I also teach these night classes because I really like it. So so I hope you guys enjoy the course. You know, maybe I will not be able to convince you to switch majors and pursue statistics. And in fact, most of you probably already have your bachelor's degree and are trying to enter a graduate program, and you have to fulfill some kind of statistics course requirement. So you probably have these careers in mind already, but I hope I guess my hope for this course is that you'll at least gain an appreciation for it. And many of you will read some research articles, and I hope when you read the research articles, that section on the statistics and the analysis will take on a deeper meaning rather than just kind of this being a section that you gloss over and say, and then you jump to the conclusion. So, so anyway, that's what we'll do, and so we'll start with just kind of this very basic question of, why do we study statistics? Okay, and so my argument is that we study statistics to gain a better understanding of the world around us. I hope my handwriting is legible enough for you guys to read and take notes on. At least you have the advantage of me kind of saying what I intend to be writing up on the board. So to gain a better understanding of the world around us, and in particular, statistics, the subject, allows us to make conclusions from limited data. Okay? And what I mean by that is that usually we have some kind of research question. Okay, so we have a research question or a statistical question. Okay, and these are questions that pertain to a group rather than individuals. Okay. Okay, and whenever you have a group, you're going to have variation within the group. Okay, so variation exists within groups. Okay, and so you're trying to kind of ask a question kind of about the group as a whole. So it can just be something like, what percentage of U.S. voters will vote for the Democratic candidate on whatever day. Okay, so that's looking at the group would be U.S. voters. There's variation. You're going to have people who vote for the Democratic candidate, people who don't. And we're asking a question, what percentage will vote this way, okay? Or, we could say what percentage will vote for the Republican candidate or the, other party candidate. All sorts of stuff. That's just, one topic. It could be, is an experimental drug more effective at treating some disease than the current existing treatment? Okay, and we can talk about how these questions can be answered. Okay, so just example questions. What percentage of this new experimental drug more effective at treating, disease Y than the existing okay. And so to answer these questions, to get the true answer, we have what we call a population. Okay, and so the population, this is everyone who is relevant to answering our statistical question. Okay, and so the population for this first question would be all U.S. voters. Okay, everyone who's going to vote, and that would be some many millions of people. Okay, that would be the population. Is this new experimental drug more effective at treating some disease than the existing treatment? The population there would be everyone who is affected by the disease. Okay, and in either case, the population is generally too big for us to study directly. Okay, either the people are too hard to track down every single person with this disease, or maybe there's just too many voters for us to count except on election day. Okay, so these are the population. This is too big. Too big to observe directly. So how can we answer these questions if we can't look at the population? Well, what we do is we just take a small little piece out of the population, and this piece is called a sample. Okay, and so the sample, maybe this is 600 people or 1,000 people. This is a small group that we can observe, so So let's say there's 600 people in this group. We take a sample, and then we study this sample. And in our ideal situation, the conclusions we make from the sample can then be generalized to the population. Okay, so I hope you guys can see that. Let's see. Okay, may I flip to the next slide? Oh, looks like some of you guys are still writing. So yes, so in statistics we study only samples, but based on our understanding of probability and mathematics in general, I guess, the conclusions that we make from a sample can a lot of times be generalized to the population. Okay, so all right, so for conclusions based on a sample to be valid, the sample must be representative representative of the population. Okay, and so one way that we can select a sample that should give us representative samples is through simple random sampling, okay, or SRS. Okay, and the idea behind simple random sampling is so let me actually okay, so we have a sampling frame. Okay, and the sampling frame is just a list of individuals that we will sample from. Okay. And in our ideal case, the sampling frame is a list of everyone in the population. Okay, so ideally, okay, but this is often not possible. So anytime you have a population that's bigger than just one institution, so let's say you just want to do like Los Angeles County, or even the city of Los Angeles, or just even, you know, pick a smaller city, it's very difficult to get a list of every single person in that city, just because not everyone has a permanent address. Some people are kind of hard to track down. Who counts as a resident? These are all tough things, and so a lot of times your sampling frame isn't a perfect list of everyone in the population, and so the quality of your sampling frame is going to affect the quality of your sample. Okay, so if your sampling frame, for whatever reason, does not include you know, a certain group of people, then your sample will not include that group of people either, and you know, and that could affect the results of your study. Okay. So you know, so if the sampling frame is of poor quality, your sample will suffer. Okay, But ideally, you have the sampling frame, and it's a list of every single person in the population, okay? And so simple random sampling is very simple. You just randomly select individuals one at a time. From the sampling frame, okay? And this mathematically, this makes every single possible sample equally likely to be selected. Okay. So, you know, if you were to list off every single possible sample that could be possibly selected, using simple random sampling would make every single one of those possible samples equally likely in being selected. Okay. You know, there's all sorts of practical problems with trying to pull off a simple random sample. So first off, getting a good sampling frame is difficult to pull off. Even if you have a perfect sampling frame, when you randomly select individuals one at a time, you might not be able to get a hold of those individuals that you have randomly selected. So, you know, maybe you're trying to reach people by phone. Not everyone picks up their phone. You know, or you might be able to reach them and you say, hey, can I ask you a few questions? And they say no. Okay? So pulling off a truly simple random sample is actually very difficult to do in real life. Okay? And so there are research organizations like Pew Research and you know, Gallup. These are very well-respected research organizations, and they have spent a lot of time and energy trying to figure out how can we get representative samples and overcome these practical problems. And the answer is there's no easy answer, okay? And so, you know, in an election year, we see all sorts of poll results being shown on TV and things like that. But the truth is a lot of these poll results have really high margins of error because it's really difficult to get truly representative samples. And so you always have to take these things with a grain of salt. It's difficult to do. We have other sampling methods. Well, here, let me just, so, you know, with people it's really hard. But, you know, random sampling from, you know, names out of a hat is easy, right? If you have 30 names, you can put them on a piece of paper, you can throw them in a hat, mix it up, and pick them out. Okay, that's easy. Let's say you had, I don't know, mice in a cage, okay, and you wanted to randomly select 5 mice in a cage, okay? Can I just close my eyes, reach into the cage, grab a mouse, and do that 5 times, and would that give me a random sample? Yes? No? Maybe? What's what do we see? The if you say no, what kind of problems do you see with me closing my eyes and just kind of feeling around and pulling out a mouse?
Well, are you putting them back in, or are you just?
That doesn't matter, but yeah, it doesn't matter if I put them back in or not. So these are things that we don't often think about, but if I were to just reach in and grab a mouse, I'm going to have a higher probability of selecting slow mice or less responsive mice than ones that are alert or faster moving or things like that, okay? And so, depending on what study you're performing, that might influence your results. And so to get a random sample, you would have to number every single mice in the cage. So if there's 20 mice, you have to number them 1 through 20. Then you need some kind of random device over here, whether that's a computer that randomly picks numbers out of the list of 20, or you put the numbers 1 through 20 on a piece of paper and shuffle them up in a hat, and you pick those numbers, and then you select the corresponding mice from the cage, okay? And that's the only way you can get a truly random sample, because just reaching in there and grabbing whichever mouse was easiest to grab is not going to give you a random sample. And so, probably many of your high school projects or whatever you might have done probably did not have truly random samples, and these are just things you have to be aware of. If you do any kind of study poll or survey online, you are not going to get a random sample. Online surveys are notorious for being easily manipulated, and also only people who, oftentimes only people who have very strong opinions about certain issues are the ones who are going to respond to your online poll, okay? So I always cringe whenever I see some larger organization, conducting a survey saying like, who should we select for this, or where should we do this, or whatever. And so I think there's always just kind of like funny results where it's like, send Justin Bieber to North Korea or something like that. These are that happened a few years ago, and it's just, when you do things online, you can only expect stuff like that to happen. So you can take an entire course on sampling methods. We're going to talk about it maybe about 10 minutes in this class right here, and that's it. A lot of the math, when we go through our course, this is taking a very classical view of statistics, okay? So, we do things by hand, and we kind of just assume that our samples have been picked via random selection methods. So just be aware that in the real world, sampling is a very, very difficult thing to do, okay? So I'm going to just mention a couple other sampling methods that exist, okay? So, and they are also mentioned in our book. Other sampling methods, okay? And so we have the stratified random sample. And with the stratified random sample, that the population consists of subgroups. So, for example, maybe the population that you're interested in, maybe that it has this percentage of this race, this percentage of another race, and things like that. So so for example, the population is 30% race 1, 20% race 2, etc., etc. Okay, and so when you select your sample, you force your sample to have these same proportions. Okay. You know, the risk here is if your information about the proportions that exist in the population are wrong, then your sample is going to be wrong as well. So, but that's the stratified random sample. Okay, and then another method, sampling method. This is called cluster sampling. And in cluster sampling, we have subgroups in the population. We can get a list of all of those subgroups. So in these subgroups, these are called clusters. So, you know, maybe you have 300 subgroups, okay? And then we randomly select from that list of subgroups. So we randomly select, I guess, clusters from our list of clusters. And then we survey these selected clusters. Okay, and so these are just other sampling methods that exist in the world of sampling. Again, in our class, we're going to just kind of assume that the samples we've selected have been selected randomly, simple random sampling. Okay, so in our course, we assume our data via simple random sampling. Because the mathematical properties that the assumptions that go into making the math work depend on this assumption of simple random sampling. Okay. But again, always keep in mind as you're reading studies. So with studies, how do they select the people? Is it reasonable? So the studies that you get will never be a truly simple random sample. It's just not possible to do. But the question you should be asking is it reasonable to believe that the sample that they are studying could be representative of the population about which they are making conclusions? Okay? So if it's reasonable, then sure, you can go on and believe the results of the study. But if the sample that they are looking at is no way representative of the population, then the results of that study are just not going to be valid. Okay, if someone did a study on what movies are popular, and the only people they surveyed are I don't know, kids who go to UCLA or something, then the opinions of this study will not be representative of the entire country or things like that. So just whatever the case might be, you might not be able to pull off a truly random sample, but it has to be reasonable to conclude that the sample that they're dealing with is somewhat representative of the population about which they're making statements. Oops. Sure. Okay. Let's see. We'll talk about gathering data. Okay. And so from a statistical standpoint, we can we have anecdotes. We have observational studies. And we have experiments. Okay. And so anecdotes, these are just individual stories. You know, these are kind of stories from individuals. And I don't want to discredit anyone's individual story, but as far as statistical analysis goes, we can't do anything with anecdotes. Okay, so from a statistical standpoint, we cannot use anecdotal data. Just because people who have stories, these are not going to be individuals representative of the population. There's just nothing we can do. Okay. So we have observational studies. Okay. With observational studies, we observe our participants, okay? Okay, we do not interfere. So we don't interfere with the participants. We do not assign treatments. We generally, we allow the participants to kind of pick their own set of conditions. Okay. And so at the end of an observational study, we may see that one we may see that one set of conditions is associated with another, okay, or that one set of outcomes is associated with a particular group or a particular set of conditions. So we may see that a particular outcome with a particular set of conditions. Okay. If that happens, all we can say is that these two outcomes, that these things are associated. We cannot say that one causes the other. Okay, so we can only say that there is an association. Okay, we cannot say that one causes the other. That one causes or is caused by the other. Okay. So, so for example, there really was a real study, and it said people. This was the result of a study. People who drink diet soda I guess have a much higher incidence of heart disease than people who do not drink diet soda. Okay, and then so after this study was released, all these just different websites sprung onto this and said, diet soda is terrible. Aspartame, which is one of the primary sweeteners in a lot of diet sodas, is bad for you, and you're going to have heart attacks and things like that. But those would be incorrect conclusions to draw from this statement here. Okay, and really this statement is not very useful at all. They might just as well have said unhealthy people are unhealthier than healthy people, or something like that. Okay, because in general, those people who choose to drink diet soda well, maybe I shouldn't even, I can't even say that. People who maybe have a higher risk of heart disease to begin with. So if we think of people who are overweight or obese, these people have a higher risk of heart disease. These people are also more likely to drink diet soda than non-diet soda. Okay, and then if you also think of other people who are very healthy, okay, people who are into fitness and eating healthy or whatever, they are less likely to drink diet soda in the first place. Okay, and it only takes just small changes between groups within the population for these types of differences to become noticeable. Okay, so it's not necessarily that diet soda is causing higher risks of heart disease or anything like that. It's just people who have a higher risk of heart disease to begin with are probably more likely to drink diet soda than those people who do not. Okay, so the possible explanation, and so there could be a million explanations. Maybe one of the explanations is that diet soda actually does increase the risk of heart disease, but we can't conclude that just from seeing this phenomenon alone. Okay, so one possible explanation is that people at higher risks of heart disease are more likely to drink diet soda. So, so anyway, this is what we have from observational studies. And so, if you muddy the excuse me, the results or the study enough, it can be tempting to draw these types of conclusions. Okay, so always kind of keep this in mind. We didn't force anybody to drink diet soda. We didn't say you have to start drinking diet soda, and then we're going to see what effect this has on your health. We just said, okay, we're going to just look at people, and we'll see what difference things make. Okay. Is that okay? All right. And on the other hand, we have experiments or controlled experiments. And with controlled experiments, the researcher will try to control as many aspects of variation as possible. Okay, the researcher assigns treatments usually randomly to the participants. So the researcher will assign treatments to the participants, and in the ideal scenario, okay, all other aspects of variation will be made identical for all participants. Okay, now of course we can't control every aspect of every single person's life, that even for those who participate in the experiment, but ideally we could. So maybe we want to know, is a certain drug effective at reducing cholesterol? Okay, and so we would have to think, what are all these the different possible things that could influence cholesterol? And ideally, if we have 100 participants, 50 of them would get the cholesterol drug, 50 of them would get some kind of placebo, and then ideally we would say everybody would be on the same diet, everybody would have the same amount of exercise, everybody would get the same amount of sleep or whatever, and have this whatever, anything that could affect cholesterol. Everybody would be exactly the same, except this group gets the drug, this group gets the placebo. Okay, and thus at the end of our study, if we observe any difference between this group and this group, the difference between cholesterol results at the end of the study can be attributed to the fact that this group got the drug and this group did not. Okay, that's in our ideal scenario. So at the end of the study, if we observe differences in outcome, between treatment groups. That difference can be attributed to the difference in treatments. Okay. But, you know, so experiments are not always possible. So actually, so let me just say, so with a properly done experiment, we can make cause and effect conclusions. Okay, of course, if supported by data. Okay, but experiments are not always possible for they're not always possible because of ethical or practical reasons. Okay. So, you know, if we wanted to know, does smoking cause lung cancer, we couldn't perform an experiment. We couldn't say, thank you for volunteering to this experiment. We've randomly assigned you guys to two groups, and in group A you have, thank you for volunteering. Starting tomorrow you're going to smoke a pack of cigarettes every day, and we will see whether you develop lung cancer in 10 years. We're not allowed to do that, and so, you know, we couldn't do any kind of experiments like that. And because no experiments could be done, the tobacco industry often argued against these cause and effect conclusions, and they say, oh, sure, we're not disputing that, that those who smoke develop lung cancer at a much higher rate than those who don't smoke. However, you have the conclusion all wrong. The real reason is that these people have a genetic predisposition for developing lung cancer, and that's what causes them to pick up smoking in the first place. They're looking for something to soothe their lungs, or whatever, you know, whatever they wanted to say. And, you know, from a statistical standpoint, just looking at the data, you cannot argue against some kind of explanation like that, that manages to explain two phenomena happening together, if you've only done observational studies. Okay. Today, the tobacco industry admits that smoking is bad for lung health, but you know, it took a long time to kind of get there. They had to do studies on, like, there's like twin studies, people who have the same genetics and things like that. And so anyway, okay, so that kind of covers some of the basics of chapter 1 in our textbook. You know, make sure you do your reading, which covers, you know, some of these important introductory concepts in statistics, you know, that are very important. And again, in our class, we're taking a very classical view, and so, you know, we've spent maybe an hour total on some of these topics, but you could take an entire course devoted to sampling methods. You could take an entire course devoted to survey, observational study research, how things should be properly done, or even how experiments should be designed. We're not going to get into some great detail there, but so just make sure you do your reading from chapter 1. With that, we'll start diving into chapter 2, which is on descriptive statistics, and I kind of just want to, at this point, kind of give maybe a roadmap of how different topics in our class will tie together. Okay, so kind of this is a statistics course roadmap. And so, so today we will cover descriptive statistics. Okay, and descriptive statistics, it's all about kind of being able to describe a large set of data with just a few succinct summary stats. Okay, so you know, this is kind of all about being able to describe data with just a few key points. Okay. And then next week, we'll get into probability rules. Okay. And these start off with some basic rules of probability, and we'll build off of that into the following week, which will have probability distributions. Okay, so in particular, we'll learn like the normal distribution, the binomial distribution. Okay, and after we understand probability distributions, this will come to sampling distributions. Okay, so sampling distributions, this is understanding kind of the probability of getting particular samples, or probability of getting samples with certain properties. Okay, so this is the probability of getting a particular sample of data. Okay, so we understand kind of learn these probability rules and how probability distributions apply to get sampling distributions. Okay, and then so now we then and this will be right before the midterm. Sampling distributions and descriptive statistics come together to create statistical inference. And we take our understanding of sampling distributions and the fact that we have descriptive statistics for a sample, and we ask, could this sample that I have with these particular properties, could this have been a result of random chance, or is it rather evidence that something interesting is happening in our population? Okay, so we say, you know, could the data I have, or could the sample I have with, you know, these properties result of random chance. Okay, so this is a statistical inference, and we will learn just many statistical inference topics, or statistical inference tests. Okay, statistical tests. Okay, and so this includes, so after the midterm, we're going to just cover all of these different tests. We have the t-test. This is called the chi-squared test. We'll cover one-way ANOVA. And we'll cover correlation / regression. And we'll have one non-parametric test. Non-parametric Wilcoxon. Okay, and so this part will take us up to the midterm, and then after the midterm, we'll focus on just a bunch of different statistical tests, and these are kind of where we're headed. Actually, okay, why don't we take a 10-minute stretch break here, and then we'll pick up at maybe 8:22 and finish out chapter 2.